This is part 2. We now move from the first principles of tensor algebra into Voigt notation, principal stresses and strains by hand, and standard elasticity problems for every key topic. We will follow one rule. Tensor notation first, indicial notation second, and numerical example third. We keep one stress tensor, one small strain tensor, and one unit normal throughout the video so the algebra stays visible and the notation remains consistent. In Voigt notation, a symmetric second-order tensor is stored as a 6-component vector. For stress, we list the tensor components directly, while for strain we use engineering shear strain components with the factor 2. That factor of 2 is not optional. It is exactly what makes the double contraction equal to the Voigt dot product. Principal stresses come from the eigenvalue problem. We first write the tensor equation, then its indicial form, and only then the numerical roots of the characteristic polynomial. Once the principal stress is known, a principal direction follows from the homogeneous linear system. The same eigenvalue idea applies to strain. Again, we show tensor notation first, indicial notation next, and then the numerical principal strains. In the first elasticity problem, strain is given and stress is required. For isotropic linear elasticity, we first write Hooke's law in tensor form, then in indicial form, and then substitute the numerical Lamé constants and the strain tensor. In the reverse problem, stress is given and strain is required. The compliance form is the inverse constitutive map, and the tensor shear strains follow from sigma ij over 2g for off-diagonal components. Traction is the stress tensor acting on a plane normal, while strain energy density comes from the double contraction of stress and strain. Again, the sequence is tensor form, indicial form, then the numerical evaluation. We end part 2 with plane stress and plane strain. Each is a different constitutive reduction. We first state the tensor or matrix form, then the constraint in component notation, and then the numerical stress response for the same in plane strain vector. This completes part 2. The essential progression is now clear. Voigt notation, principal stresses and strains by hand, worked elasticity problems, and the distinction between plane stress and plane strain.